Hey everybody. As I mentioned in class on Wednesday, we've got one more topic to cover before spring break, and it is a fairly significant topic. The topic is use substitution, and my plan is to give you a good look at it here in this video, and then we should be able to get together again on Monday and cover some different aspects of it, see a few tricks of the trade, get you guys ready for the next quiz. I know you just finished a quiz, and the next quiz is in 1 week, but that is the fact. That's the way it is. And at least the positive side of that is that you don't worry about studying for something over the long week. Although I suppose it is a gateway quiz, so I guess that week may be spent doing a little bit of studying for people who don't pass the first time. That's a great positive message to start this video, right? Well, let's get into it. Substitution, sometimes known as U substitution. As you can see, it's a useful technique for evaluating more complicated integrals. And I might add on that this is our way of undoing the chain rule. Those of you who, in class on Wednesday, you saw a little bit of how this works, but I'll go through. I'm going to pretend like you don't know anything about this topic. I'm going to start with the hypothetical situation here. I've got the integral of the square root of x dx, which of course we could write as x to the 1/2. And so our antiderivative, a nice simple undoing of the power rule. Increase the exponent by 1, and then the 2/3 undoes the 3/2 when we take the derivative. Nothing new here, but just my way of leading into this. If I say the integral of the square root of x dx is 2/3 of x to the 3/2 plus c, well, if I change my variable and if I say what's the integral of the square root of t dt, well, it's the same thing. It's all exactly the same stuff. It doesn't really matter what that variable is. I could keep going and substitute every letter of our English alphabet or the Greek alphabet, or I could even make up symbols and use those to stand for the variable. It doesn't matter what that variable is. And I guess this is kind of the key one. As we do use substitution, the fact that we know what the integral of the square root of u is going to be helpful with the first example that I will be doing with you here today. That example being this. So I've got a little bit more complicated integral. And when we've seen things like this so far in this chapter, I've said we can't do this one. We don't know how to do this one. We have to manipulate this into a form that we know how to do. And that's still true. We don't know how to do this. The idea of substitution is let's take something that's complicated and simplify it, replacing part of that complicated expression with something that's a lot simpler. Again, I mentioned this on Wednesday. When there's something inside of a function, that's probably a good indication that that stuff is what we're going to end up substituting. So for the one we're looking at here, I can take that 3x squared minus 4 out of there and replace it with what it is equal to, the u. I guess I'll put this here. I'll hide it in plain sight. Now, unfortunately, this gives us this kind of weird integral where I've got both x's and u's. This dx, remember the dummy variable at the end tells us that we're anti-differentiating in terms of x. And so now I've got this other variable there. This bad mixes of x's and u's makes this undoable. I've got two different variables. And while multivariable calculus is a thing, it doesn't look anything like this. So instead of just doing that, we're not just going to find u, but our choice of u is going to dictate that we also have du. Think of a du as the derivative. It's actually something called a differential that we studied. I don't even remember when. It was either late first semester or early second semester that we looked at something like if u is 3x squared minus 4, then du is what? And this actually comes from the idea that if I say u is 3x squared minus 4, if I take the derivative in terms of x, du dx, Leibniz notation would say that du dx is, let's see, I guess that would be 6x. So technically speaking, I probably shouldn't say this, but if I multiply both sides of the equation by the dx, I get du is equal to 6x dx. which very conveniently on this problem shows up exactly in that form. Now, it's not always going to work out this nicely, and I'll do a couple examples of that before we're done here today, but sometimes it does work out that nicely. As you're doing homework problems, you'll hope for things like this, where, gosh, the derivative of this stuff is the stuff that's outside. That's a really convenient thing when that happens. Now, I'm going to do the substitution on this color-coded slide so you can easily see where I'm making my substitution. So again, choosing u to be the stuff that's inside the radical, u is 3x squared minus 4, means that du is 6x dx. That's going to be a really nice substitution. I can take that 3x minus 4 out of there and replace it with the u that it's equal to. I can take that 6x dx out of there and replace that with what it's equal to. Don't put it here. This is not correct. You'll never see it like that in any textbook because it is not correct. Put it at the end. The du is the period at the end of the integral sentence. And so here we go. This is the integral that we saw previously in the hour. The integral of the square root of u du, that's 2/3 u to the 3/2 plus c. It's still going to be the same thing. The integral of the square root of u du is 2/3 times u to the 3/2 plus c, which is great, except for the fact we were asked for an integral of a function of x. Our integral was the integral of 6x times the square root of 3x squared plus something dx, and my answer is this thing that's in terms of u. But fear not. In fact, if we were meeting together, if this was not an asynchronous lesson, I would probably pause at this point and say, any ideas about how we can handle that? At which point someone would probably say, resubstitute. U is 3x squared minus 4. And so I can take that 3x squared minus 4, I can plug it back into the expression in place of that u. I've got my answer. The integral of 6x times the square root of 3x squared minus 4 dx is 2/3 times 3x squared minus 4 to the 3/2 plus c. How could we check that? How could we verify that the integral of this stuff is equal to that stuff? And again, if we were together, I would pause and say, any ideas about how we would do this? And of course, somebody would promptly say, we could just take the derivative of our answer and make sure that the derivative of our answer is what we had at the beginning. It is the integrand from our original integral. And of course it is. I've got the work shown here. If this is my function, the derivative, let's see, 3/2 times this stuff to the positive 1/2 times the derivative of the stuff inside, the 6x, 3/2 times 2/3 cancels out. And I just rewrite this in the form that it was. So it does work. This is legitimate mathematics that I'm showing you today. All right. As I mentioned before, sometimes it doesn't work out quite so nicely. As I look at this one and I say, what are we going to choose for our u and our du? Well, as I mentioned before, the stuff inside a function is usually a pretty good bet. So I'm going to let u be x to the 3rd power. If u is x to the 3rd power, that means du is 3x squared dx. And this doesn't quite match up with what we've got. I can take that x cubed and replace that with a u, so that part's okay. I've got x squared dx, and golly, it would be nice if I had a 3x squared dx. But I don't. There's a couple different ways we can do this. One way is to manipulate the integral into a form that looks like my substitution. The other way is to manipulate the substitution until it looks like the integral. And I honestly have probably done both methods about the same. Sometimes I'll leave it up to a class. This time I'm choosing to do it in the way that I just did with my Calc BC classes a little while ago. And that is, I'm going to manipulate this until it looks like what I want. I want x squared dx, and I've got 3x squared dx. So I'm just going to multiply this by 1/3 and say that 1/3 du is equal to x squared dx, which is what I want. And so now I can make my substitution. I'm just going to move this down here and say that this integral of x squared times sine of x cubed dx, let's see what this looks like. Replace the x squared dx with a 1/3 du. I'm going to throw that 1/3 on the outside. You don't have to do that right away. If you want to have it in the integral, that's fine. I'm going to put that du way at the end. Of course, I would never put that du anywhere except at the end of the integral. That takes care of that part. All I have left is sine of x cubed. My substitution is that x cubed is equal to u. And so there we go. I've gone from an integral that's difficult, complicated, not impossible, but complicated. I've made it into something that we've been doing for a while at this point. I'm going to just keep that 1/3 carried on. Let's see, the integral of sine of u, the antiderivative of sine of u, let's see, the derivative of sine is cosine. So the antiderivative of sine must be negative cosine. I'll put that negative in front of this. Of course, don't forget your plus c. And then finally, this is a good expression, but in terms of u, so let's resubstitute. U was x cubed. So my answer will be negative 1/3 cosine of x cubed. And as always, if you're skeptical, if you doubt that this works, go ahead and differentiate it, and you will find that we end up back where we started at x squared times sine of x cubed. So here we go. Another good example. Just a few more that I want to go through that are a little bit more on the tricky side. I take that back. This one's not all that tricky. But I think worth us taking a look at. And I know that when I've given this problem in the past, sometimes people will look at it and say, well, couldn't we just multiply it out? And yeah, sure you can. You can do that for this one. But as soon as I put an exponent of 8 on top of it, all of a sudden, well, I guess you could expand that too, but that's going to be a monster. It's going to be a disaster to try to do. So, you know what? Maybe I'll just keep it like that. Let's do this one. Let's keep that 8th power up there. It's going to make this one no more difficult to do as a substitution problem. It would be decidedly nasty if we did it expanding this whole thing. So what is u? What is du? Parentheses kind of give it away. It's probably the stuff inside here or the stuff inside there. As I think ahead, not only do I need my u to show up and be substituted, du needs to show up also. So if I had u is this stuff, my du doesn't match up with the other expression that I've got at all. So I'm going to let u 5x squared minus 15x plus 7. That way my du will be, let's see, the derivative of that would be 10x minus 15 dx. It doesn't match up perfectly with the rest of this stuff, but boy, it's convenient. This stuff is exactly 1/5 as big as that stuff. By the way, if it didn't work out that way, if it wasn't off by a nice constant factor, that means I'm doing something wrong. That means I'm doing something that doesn't make sense. So this one works. We'll be able to do this. I'm going to, let's see, multiply by this a fifth and say that 1/5 of du is exactly what I need. 2x minus 3 dx. Now I'm ready to make my substitution. I'll replace this stuff with u. I'll replace this stuff with 1/5 of du. I'm worried that I misspoke there. This stuff is u, and the second set of parentheses in the dx, that is my 1/5 du. So I'll replace that one, or that stuff at the end. I'm going to put the 1/5 outside the integral. That's kind of what I do when I have these problems. So that takes care of the 2x minus 3 dx. Replace that with 1/5 du, 1/5 on the outside, du at the end. And then I just have u to the 8th power. That's not too bad. Anti-differentiating u to the 8th power, that's just 1/9 u to the 9 plus c. and then I can resubstitute. I'm going to go ahead and multiply 1/5 by a 9th to get 1/45 of, what do we have? U was 5x squared minus 15x plus 7 to the 9th power plus c. Not very obvious that the derivative of this would end up being what we started with. If you don't believe it, go ahead and try it out. This is correct. I think I'm going to skip this one. This one's pretty similar to what we just did. But let's take a look at this. I'm going to head off a misconception before you guys have a chance to make it. I've mentioned a few times in the last few weeks that if it looks like a heart, we can take it apart. So if I had something like this first one, I could just take this and split it up into two integrals, make it x squared over x, which is just x, minus 1 over x. And this integral doesn't require any substitution. The antiderivative of x is just 1/2 x squared. Antiderivative of 1 over x is the natural log of the absolute value of x. So we've seen these. That's no problem. This one, not so much. But now that we have u substitution, we have a way of doing this. Now I've said look for the stuff inside a function. We don't really have a stuff inside, but we do have a numerator and a denominator. In the case of this one, I notice the derivative of the denominator is a multiple of the numerator. It's not exactly the numerator. The derivative of x squared minus 1 would be 2x. And so we're off by a factor of 2. I can deal with the factor of 2. Let's let u be x squared minus 1. That means our du is 2x dx. All of a sudden, this one doesn't look all that bad. My substitution is exactly half of what I'd like it to be. It'd be nice if it was x dx. I've got 2x dx, so let's just put a half in front of that. 1/2 du would be equal to 1x dx. And now I've got a nice substitution. Replace the x squared minus 1 with a u in the denominator. I've got x dx. I can replace that with a 1/2 du. Let's go ahead and do that. This is going to lead us to, you've seen this 3 times already. Let's throw that 1/2 on the outside. I've got 1 over x after I do that substitution. And then where to put that du? You can put it on the top. Sometimes you'll see in a textbook it'll be du. Sorry about this. I'm replacing x squared minus 1 with u. Sorry about that. And I could say that the du is in the numerator. Du over u is a fairly common notation. If you're not comfortable with that, you can just call it 1 over u du. Just don't forget the 1. You can't have nothing as a numerator of a fraction. And then there we go. Antiderivative of 1 over u is natural log of the absolute value of u. Don't forget the absolute value. It doesn't always matter, but it is always correct. And then finally, my u is x squared minus 1, so we resubstitute. And my integral is 1/2 natural log of the absolute value of x squared minus 1 plus c. Cool and the gang. That's what we just did. We don't need to do that again. And one more twist before I'll end this video. Something that looks like this one. I don't remember if this shows up in your assignment over the weekend or if it's going to show up next week sometime, but at some point we're going to have something that looks like this. I mentioned before, if you say u is this and du is that, and it doesn't match up perfectly, the du in this case, if I let u be x squared plus 1, then du would be 2x dx. Our numerator is not half of 2x. That plus 1 really significantly messes things up for us. Well, the trick we're going to use on this one, or the technique we're going to use on this one, is probably best demonstrated by Steve Rogers here. You can take a fraction like that, this thing plus that thing over a denominator, and I can split that into 2 separate fractions. this thing over x squared plus 1 plus that thing over x squared plus 1. And then properties of integrals say that when we do that, we can split it up and have that as two separate integrals. So that's what I'm going to do here. I'm going to say that this integral is the same thing as x over x squared plus 1 plus another integral 1 over x squared plus 1. Now, as long as I can do both of these, I'll be okay. Now, this first one is basically the same problem that we just did for the previous example. It's an x squared plus 1 instead of an x squared minus 1. But the substitution is going to work the same way. So I'm going to take a little bit of a shortcut. I think this video has gotten long enough as it is already. End up 1/2 natural log of the absolute value of x squared plus 1. By the way, a case where, technically speaking, I don't need that absolute value because this stuff inside it, x squared plus 1, will never be negative. So the absolute values are superfluous, but I'm going to keep them there just because it's good practice to have those there. And then this one, the integral of 1 over x squared plus 1, once again, if we were together, I would probably pause and say, anyone recognize this as the derivative of something? At which point someone may recognize it. Most likely someone would say something like, isn't that some trig thing, like a tangent or something like that? And I would say, yeah, close enough. This 1 over x squared plus 1 is the derivative of the inverse tangent. No substitution needed for that one. And then I'm going to tack on the plus c. Technically, I've got a plus c on both of these. I'm adding two arbitrary constants together, and I'll just say that this arbitrary constant plus that arbitrary constant is some other arbitrary constant that I will call c. So there we go. Just a sneak preview. One of the things that we'll be talking about on Monday is what do we do when we've got limits on that integral. You're not going to have any of those to work on in your assignment over the weekend, so I will save that for Monday and then a couple other tricks of the trade. Get you guys ready for the quiz that will be next Thursday. All right, that's enough for that. Hope the quiz went well for all of you. I'll try to get those graded fairly quickly so that you know if the retake, or no, sorry, the quiz you just took is not a gateway quiz. I still hope you did well, but you won't have the opportunity to retake that one. So I'll stop this at this point. Have a great day, have a great weekend, and I will see you on Monday. Bye.